I want to double check that you guys are all familiar with this slide. Everyone's happy with this slide? Yeah? Does anyone want to explain that slide? Anyone brave enough? So what do we have? Yeah, go ahead, AJ.
There's validity of Hoare triples,
Yes.
right? Other syntactic constructs.
Yes.
And then on top of this, you've got a nice strengthening and weakening of pre and post conditions, respectively.
Sure, okay. Exactly. This is Hoare logic. I think almost every university teaches this, if you're doing programming languages, perhaps. But the point is you've got axioms about sort of atomics, and then you've got kind of decomposition rules about your compound statements that you develop, right? So we're treating in this particular programming language, the wild language, imp language, treating skip and assignment as being two atomics, right? And then we've got sequential composition here, got your if then else, and then we've got your loop. And then, as Jamie pointed out, there's weakening and strengthening rules, right? So what's a good way to think about? Yes, go ahead.
Shouldn't the assignment have the substitution on the right side?
That's a common mistake, but no, it's on the left.
Yeah.
Yeah. No, it goes the other way.
So what do you mean by so this P is what do you mean by P for is there any variable occurring V occurring inside P? So
Maybe.
that means okay.
Maybe. So let's explain this notation here then. This is a notation that is syntactically replacing all occurrences of V in P by E. Yeah? If V has nothing in there, if P has no V's, then you just get back P, right? So, pen, right? So, V is equal to X, being my predicate, that's my P, and then I'm going to replace V by 1, right? So that should be, what's that going to be? So this is my predicate P, this is my E, and that's my V, right? So this substitution gives me 1 equals X. Yeah, it's a straightforward syntactic substitution, right? 1 equals X, right? And if this happens to be 73 of Z, then you get 73 of Z here. Yeah? Yeah? Okay, good. So it's good to sort of brush up on things that maybe we already know. But that's what's going on. So you make the syntactic replacement on the left-hand side, and we want this triple to be valid, right? So this axiom is valid if your precondition is at least as strong as this. Okay, at least as strong as that. Okay. So what is a good way to think about what a predicate is? Now, we're okay, so I'll step back a bit. What is a good way to think about what a state is? Yeah.
Just we have to take the proposition the formula that has to be closed. Like for example, like P, does it have to be closed always? In the sense that could have free variables.
Yes. Yes.
So, what kind of logic is it? Is it like higher order or?
No. We can just think about it as first order predicates. Yeah. So think about them as first order predicates. Yeah. But they're they're predicates that are applied to a state. Okay. So given a state, you'll get a Boolean back, true or false. Okay. yeah, maybe this is a good way to sort of ground this. What's a good way to think about what a state is now in this particular setting?
Do you think of it as just a mapping from identifiers to values?
Identifiers to values, yeah, or variables to values, or locations to values, yeah. So we can think of our state space, let's call it sigma, as being, let's use Nat's idea, identifiers to values, right? And then if we have a state that's in sigma, what we can do is we can now think of our predicate being applied to some sigma, and that's going to be a Boolean, right? Right. That's kind of how we think about these things. Well, it's a good way to think about these things anyway in this sort of setting. Yeah. Everyone happy with that?
I'm trying to make sense of the axioms, like the second axiom, the substitution axiom.
Yeah.
So I have some predicates, and there's a V happening there. That would be some V, and I substituted. So before running the program or before the assignment, actually, whatever V substituted E, and when the assignment after the assignment happened.
You get back E.
V gets substituted inside. Okay.
Yes. Okay. Okay. So are we happy with that?
Yeah.
In general? Yeah. Okay. So now I'm going to jump to. Like I said, this is made up slides, right? So I'm going to jump to, I think. Oh gosh, I wish I'd. Okay, no, it's definitely here. I'm going to jump to concurrency. Okay. I'm going to jump to concurrency, and don't worry about anything at the top. But now, so this that Hoare logic obviously allows you to reason about sequential programs, and what we want to do is we want to think about concurrent programs. Okay, so we want to think about something along the lines of you go S1, S2 in parallel with some T1 followed by T2. I mean, this could be an if then else, or that could be an if then else. That could be a loop or whatever. Yeah, but we're thinking of this new operator parallel, right? And now we're going to annotate. Just as we did before with some precondition P1 and another assertion P2, and maybe I'll use different colors actually, but given that I've got them. So there's my P1, P2, P3, and then Q1, Q2, Q3, okay? And maybe you've got kind of an overall precondition P up here for the whole parallel composition, and then you've got an overall Q over here. That's the postcondition of the entire parallel composition, right? And these happen to be assertions inside a thread, okay? And these are also inside this thread, okay? And this is the parallel execution of these two programs with those assertions in there, okay? So now the question is, how do we think about the correctness? Yes, go ahead.
So sorry, just a quick question. Is notation-wise, there's no ordering being implied by the P and the Q on each side, right? It's just notation-wise. One of them being P's and the other one being Q's. There's no order implied.
No. This. Okay, so what I'm doing is I'm going to execute these two threads and interleave them.
Okay.
Okay. So how do you mean by some order?
I was just wondering if it was P for precondition and Q for postcondition.
No. It's a P and a Q. It could be X, Y, Z. It could be whatever you want. Yeah, apples, bananas, doesn't matter. Okay. Now, who knows how to think about this? The correctness of this annotation. So the Hoare logic gives you this part, right? it allows you to think about, so pretend that I didn't write anything on this side, right? Hoare logic allows you to think about the correctness of this sort of proof outline, right? You've got some precondition of a sequential program, you execute the sequential program, and then you end up with some postcondition, right? Now, I've got a concurrent program, okay? And now I want to think about, what does this mean? Hopefully you guys can see, yeah, it's okay. Yeah. So what's a good way to think about? Well, it's actually just here on the screen. There's two components now, because you not only have preconditions or conditions or assertions that you have to establish inside the thread. Okay, what can happen is that while you're here, the other thread could execute, right? While you're here, the other thread could execute. There's nothing kind of stopping the scheduler from scheduling the other thread at any point, right? So what happens if I'm here and the other thread executes? What's the problem? Yeah?
If it happens to interfere, there could be a race condition.
Interference, right? So interference, you think that your state, your precondition might be saying that your value of a particular variable is 7, right? So say, as an example, I'll pick a particular one. Say this precondition said that V was 7, right? And then this one, say T2 somehow changes V, and I change it to 33. What happens to my precondition? Well, it's broken. Yeah, it doesn't work anymore. Okay, so because of interference from somehow this environment, this external thread, things that were sort of locally true, what I thought were locally true, are no longer locally true. Okay, they're not valid because of interference. Okay. Okay, so we're happy with that? That happy? So now, in the Owicki-Gries technique, essentially what you need to do is somehow deal with this this problem. Okay, and what you need is not only sort of correctness locally, you also need some kind of resilience, if you like, right, against this interference that's occurring in this other thread. Okay, so that comes from these two, these properties here. Okay, so you've got this interference freedom condition from this other side. Okay. I wonder if now is a good time for a little exercise, so that you can. Okay, and so what does it mean to be interference free? By the way, what we want is to think of these predicates as being still valid after executing, say, one of these blocks. Okay, so you sort of break down your other thread into sort of the atomic components, and you want this predicate to be still valid with respect to that block. Okay, and then you want this predicate to still be valid with respect to this other block here. Okay. Now, what does that mean? So let's think about just this one. What does that mean? Let me just sort of write on the other side for fairness. It means I need to prove essentially Hoare logic triple. So for P1, I need to prove if P1 holds and Q1 holds, and I execute T1, okay, what do I need back? Yeah.
P2 and Q1?
You want P1 back, okay?
P1, Q2.
Because you want P1 to be kind of resilient against this Q1, T1. Okay?
Would
Yes?
you not want Q2 as well to hold? Or
No, just it's per assertion. Okay? So T1, and then we want P1 back. Okay, so that's saying kind of P1 is somehow invariant across the execution of this T1, right? provided that you can use the precondition of Q1 as well. I won't get into the technical details of why, but you can use that precondition.
Just to be clear, basically what we are doing now is trying to make sense of those two rules. Like
I'm showing you what interference freedom means.
Okay.
Yeah. Okay, so what other assertions do we have to check? We've got another local assertions P2. Sorry, by the way, this doesn't fully establish, because of concurrency, things grow sort of quadratically or exponentially, however. So this is showing against P1. Then we've also got another one. P1 is resilient, if you like, Q2, T2, and what do we want back? P1, yeah? So that now, if we can prove both of these things, we've shown that P1 is resilient to the interference from P1. Okay? So that says P1, I'm going to call it, if I can show both of those things, this is globally correct, if you like. Okay? Okay, so that's P1 done, if I can show both of those things. But am I done? Well, I need to also now think about P2, and I also need to think about P3. Okay, so now I go back here, and I change all of my 1s into 2s. Okay, P1s into P2s. So P1 becomes P2, that becomes P2, P2, P2. Okay, so if I show both of those things, then great, this is also is globally correct. And now we've got P3, well, no surprises. P3, 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 P3. Okay, maybe it was a mistake to write it all the way on the other side. Anyway, you get the idea. This is also GC. Okay, are we done? Are we done? You got to show resilience on the other side. Okay, so now we need to prove. So we've got question marks here. Now we need to prove those things. Okay. So far so good. We're almost there in terms of the parallel correctness. One remaining bit is, well, how do I establish this, the initial things, and how do I establish the final thing of the whole program? Okay, meaning, how do I know this was true in the first place, and this was true in the first place? Okay, well, you prove that P1 implies, P implies this precondition implies P1, and also this precondition implies Q1. Okay? And how do I know that this holds at the end? Well, I need that P3 and Q3 implies Q. Okay? And that's what this rule is saying. Okay, so this is allowing you to take your sort of external preconditions and postconditions and make them sort of thread local. And then once you have some thread local proof obligations, you've got to prove, first of all, your local correctness, which is this. Okay? Then you've got to prove your interference freedom or global correctness, which is, the reason I kind of wrote this down is in English rather than in maths is because maths is a little bit kind of annoying. Yeah. But you get the idea. Yeah? So everyone's happy with, should we go through a little exercise? I've got one for you. It's on my phone, but I've got one for you. So, and this is an example that we're going to use. Used in other places as well. So, okay, so here we go. I want to prove that y is not 1 to begin with. I want to prove that some of you who've seen weak memory might sort of already know what I'm trying to do here. Okay. That's parallel. Okay. Now we've got depends. And then here I've got okay. So I'm telling you what the precondition of the program is, telling you what the postcondition of the program is, and what we need to do is fill in these blanks here. Okay. It's not very easy to do these things, so I won't be surprised. Maybe I'll write it on this side as well. But do you want to spend, I don't know, 10 minutes thinking about this? How you could come up with these conditions to verify this little program? So we need to fill in these blanks, okay? So let's see if we can do it. If you've used weakest preconditioning reasoning in the past, one way to kind of try to derive these assertions. If you haven't, you'll just need to maybe apply some brain power. I don't know. So one way to think about it is that this is coming through this side, right? There are assertions about A and B. So you might want to think about these assertions first. So yeah, that's these assertions first. I'll also give you a couple, maybe. I'll give you that this one is sufficient to have this. Oh, you might have something stronger. Maybe that helps.
Yeah, no, we need it because the threats of
Maybe I'll also give you this one. That's just true. Who's got something? There's a lot to think about, so, but yeah, okay. This is why you want theorem provers to do the work for you, right? Well, one question is, now that I've given you these assertions, are they globally correct? Are they globally correct?
True.
Well, true is, yeah. That one? Is that globally correct?
Yes.
Yes. Yeah? Doesn't matter what kind of interference I perform on via X and Y, I still get. Okay. So, what can we try? What can we try next? Like I said, it might be easier to go through the second thread first. What would I need up here? Yeah.
If you sort of work backwards, does that become A equals 1 implies X equals 1?
Sure. Yeah. X equals 1. Okay. For the benefit of the people on this side. Yeah, that's exactly right. Okay, and so I know this bit is valid because of my substitution rule from Hoare logic, right? So I know this step is okay. Okay, yeah.
Well then, by the same, I think we can fill in the line before that.
Sure. Let me just double check that. That's what I did. Sure. Okay. Same argument here. We know that that step is valid. One thing we haven't checked is we haven't checked interference freedom. Okay. So let's do this. Let's do global correctness of this one first. Okay. Is it globally correct? Well, we said this one is GC, right? So we said is GC. This one is clearly GC. What about this one? What about this one? We're happy that it's globally correct? Yeah? Well, the only interference possible is through that assignment, okay? But what does that assignment do? It makes the consequent of the implication true. So therefore, clearly, with some logic applied, it's going to work. Okay? Yeah.
I was just wondering, with the rule as it's written there,
Yep.
do we actually need to check that intermediate thing? Because
Which intermediate thing, sorry?
so maybe I'm misunderstanding, but with the rule as written there, right, our P2 and our Q2 would be the top thing on the right hand side and the bottom thing on the right hand side.
Yeah, the way the rule is written is a little bit
Okay, right.
like the way I'm explaining is the right one.
Yeah.
The right one. The way the rule is written is just so that it fits on the slide.
Okay.
Yeah. If I wanted to kind of write a very precise rule, it would probably take a bit more space.
But what I was checking is, so the interference we need to check isn't just the pre and post condition, we need to check the intermediate.
We need to check all of the assertions, local
Right.
assertions
Yeah.
are interference free with respect to the other thread, right? And interference freedom allows you to use the preconditions that you have on the
Right.
other side. Yeah. but it happens to be the case that these can be interference-free without using those post-conditions, without using those preconditions. Okay. Okay, so this one is globally correct because the only assertion, interference possible is makes this true anyway. Okay, makes that true anyway. So this is also globally correct. Okay. What about this one? Is that globally correct? Because it now gets interference from both of the statements on the other side. Okay. So against this assignment, we're safe for the same reason as the other, as down here, right? Because, well, it interferes, but it makes the post condition, or the consequence, true. Okay? This one's a bit dangerous, because it interferes and it makes the antecedent true. Okay? Now, what do you think we can do to make this go away, make this problem go away?
Rely on the order of operations.
No, you can't rely on orders of operations. It's completely interleaved.
No, on the left-hand side, so that x equals 1 is performed before y equals 1. So assuming that that order is maintained, sorry.
Okay, yeah, that order is definitely contained. That's true. Okay. But just from pure logic perspective, without thinking about the orders of operations, so what we need to do is make that stronger. Okay, because remember, it's we want resilience of this against this. That's the problem, right? That's the problematic case that we're thinking about. Okay? And remember, we're allowed to use the precondition from this side. Okay? Previously, we haven't needed it. Okay? Now we're in a case where we do need it. Okay? And your intuition is correct. What's a good precondition that I can add here to make this
X equals 1.
X equals 1, exactly. Okay? And I know that precondition is going to help me because that precondition guarantees this. Okay? And I also know that that precondition is likely to be valid because I've got that statement. Yeah? So that's this order of operations thing. Okay. Now I'm going to give you the final one just because we've only got so much time. That's true. Okay. Just in case you guys couldn't see, what we wanted here was x equals 1, and this was true. Okay. So what's left? Well, the only thing left is to check this is resilient or globally correct against this other side. And that is trivial because the other side doesn't change x. Okay? Yes?
I might be missing something obvious, but like, why are we not just saying that P2 and P3 are x equals 1?
P2 and P3 here.
Yeah, and then Q3 is B equals x. And then you've got
There may be other valid. There may be other valid proof outlines. Yeah, I mean certainly if I put x equals 1 here, that would be okay. Yeah, but it's more than I need, right?
But then you don't need to worry about do all the implications on the other side. You could have Q1 and Q2 just be true, and Q3 be B equals x. And then with those two factors at the bottom, you have B equals x equals 1.
There may be another proof outline that's totally valid. Yeah. If you came up with a different one, I'd be curious to see it, but maybe we can check it later. Is that okay? Yeah. Yeah. Yes.
Why are we happy with the first true on the left? Because in my head, I'm like, what if y is equal to 1 here and x is...
No, why can't be 1?
I know
Because,
it can't be,
Yeah.
but we're fine with that. Like, it doesn't... I know it can't be because of the precondition at the top. But
Yeah.
You don't need it to locally be stronger.
No,
Okay.
no, that's all you need. Yeah, I'm giving you the weakest one I need because I find the weakest one is kind of neat, right? Yeah, you can add tons of stuff, right? That you know. Sure. I mean, if you wanted to, go for it. Y is not 1. Yeah. Okay. That's okay. You can do it. But the thing is, why bother, right? Now I've got something to check because now I need to check that y is not equal to 1 is. Whereas true is trivially true, right? Trivially resilient, if you like. Yeah. So I get your kind of concerns, but you can just, in a way, I think it's, for me, it's kind of nicer to have less to check, which is, and so you give the weakest one possible. Okay, and this one, I felt like this was kind of a nice kind of systematic way to work it out as well. Maybe your one also is valid, if you think about it in a different kind of way. But okay, any questions? But like, as long as you're kind of happy with this idea that this is how you lift Hoare logic, the stuff you've seen, to concurrency.
Which is decidable, let's say we have a...
Let's not talk about decidability. Yeah. So everyone happy with that? Yeah. Okay. Now I'm going to show you a scary picture. Not necessarily that scary, but a picture. Okay. It's actually not, it's very benign. Okay, there's a picture. What's going on here? What's going on here? So, can I still think about concurrency in this nice way of, well, it was a little bit complicated, but at least I could think about it as, oh, the other thread runs and it interleaves with my process, and then I'll get some interference, and then, oh, these things happen and so forth, yeah. Why does that break? Why might that break?
Depends on your memory model.
Jeremy, you've seen my talks before.
No.
Yes. It depends on your memory model, right? That's all very nice, this interleaving idea, but that works when you've got some kind of coherency across caches in memory and so forth, across maybe the cache layers and so forth, right? And you've got some RAM, that's actually where the memory address lives, and then this is kind of some cache address and so forth, right? But then you want fast caches as well. You really want to take advantage of not having to ping something very far away from your CPU. So this is the kind of architecture diagram, or roughly, that people are staring at these days. Okay, so this was just from like 2 seconds. Might not even be very accurate. 2 second search on Google for the Intel architecture diagram. But what's happening is now you've got some local caches in which you can store intermediate computation that might not be seen by another thread running on another core. Okay, so you can think of these certainly on the Intel machines as being some kind of FIFO buffer. Okay, and this CPU, when it performs a write, it goes into this buffer. Okay, but that write isn't necessarily seen by the other side. Instead, what happens is it sort of sits there, and eventually the hardware or the programmer decides that they want to evict this value. Okay, comes into one of the lower levels, and finally it can be seen by the other thread. Okay, so this is the effect known as weak memory or relaxed memory. Okay, and you have all sorts of kind of quirky behaviors. Now let me show you one for this particular memory model, this TSO memory model, which is called total store order. It allows I'm not going to write the intermediate assertions. Okay, So say X and Y are sort of global variables. This is running on one core, and this is running on a different core. Okay? And I've got an assignment updating X to 1, another assignment updating Y to 1. Okay? Those are going to be cached locally. Okay, so the other thread doesn't get to see it. So now if I read Y and I read X, it could be, right? It could be that at the end of the execution, A equals 0 and B equals 0. Or dot, dot, dot. There's not, sort of the normal interleaving semantic still applies, but you get this new behavior that was not previously possible. Okay? Sorry, this really does require me to rewrite things. So just for your benefit, you've got at the top, and okay, the program executing is X assigned 1, Y assigned 1, A gets Y, B gets Y, B gets X. Okay, so this is called the load buffering. It's actually, sorry, the store buffering example. Load buffering is a different one. Okay, who's seen this before? Yeah, okay, yeah. Okay, great, okay. So the dot 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 is the classical behavior, the interleaving behavior, okay? The new behavior I've written down, 0, 0, is the behavior due to this processor. Okay, it's the hardware breaking things. Okay. Great.
Can I ask a question, Brijesh?
Of course.
So, do you know on different architectures you might see different kind of results?
Yes.
Do you see different results kind of non-deterministically on the same architecture?
Yeah.
Okay. So really, you can't predict what the result's going to be.
Yeah. I mean, this was the problem that Peter, Sol, and John O'Glav and all these people had for a long time to validate that the models were accurate.
Yeah.
So sometimes you actually have to sort of, even though the classical example looks like this, and this is the behavior we know is possible, in reality, when they were looking for this sort of weak behavior, you kind of had to manipulate these examples a little bit. Because, a processor can execute this in instantaneously, right? It's like 4 instructions. Kind of. So it could be that one branch lets you go in one direction, if that's your question, and another goes in another direction.
So I think the way low-level programmers go around this is they just put fence instructions.
Absolutely. Yeah. We'll talk about fences in a second.
Sorry. I'm stealing your thunder. Sorry.
No, that's okay. Okay. Yes. So in fact, that's a good point. I was actually not going to talk about fences, but what you can do is to prevent the bad. I'm going to call this a bad behavior because it's unexpected behavior. Okay. So you add fences in here, or like. An M fence to be more precise, right? So you put fences in here.
So what's the semantics of M fence?
It's I won't get into this because this is not what I wanted to talk about.
Oh, sorry, I guess shut up now.
Okay, so you put that there, and then this bad behavior is gone. Okay, same on the other side. This is just okay, right. So this is the low-level architecture model, and then you know that there's tons of. Maybe you do know, maybe you don't know, but different processors have different memory models. So the one I've got here is a TSO one. Depending on how your processor is configured, how your memory and the caches are configured, you might get different memory models. So ARM have a different one. PowerPC is different, and so forth. Okay. But then now you've got kind of this. Let's call this ISA memory model. Okay, so the thing that I want to talk about is slightly higher up. Okay, so this is the ISA memory model. I want to talk about not this level. Okay, I want to talk about, well, a particular memory model called RC11. Okay, so it's the C11. What the R stands for repaired, because it was an attempt to repair the C11 model as described was actually broken. Okay, and this is like a language level memory model. Okay, and the idea is that programmers don't program in assembly generally. Programmers write C or Rust or whatever, and you want that to be compiled down to an ISA so that the sort of compiler sort of takes care of all of the fences and all these things. Okay, but what we want to do as programmers is we want to think about programs at the level of the language memory model. So if you're familiar with the language memory model, then things should be fine. Okay, okay. But this is about verification, right? So we've got a verification story to tell here, and the question is, how do we do that? Okay. Well, first of all, I'm going to show you the C11 memory model, and show you that it's a little bit it's rather complicated. There are a lot of sort of ins and outs, but I'll only show you a couple kind of features of it. And then there's sort of the verification story, and how does it link with the Owicki-Gries story that we've seen already? Okay, that's kind of where we want to go. Who's still following? You're all following? Yeah. Who's not following? Okay, good. Radio. Gosh. Okay. No, that's the wrong one. I'll even show you some Isabel so to show you this all works. Okay, so things come around in circles because I actually gave this talk at a VETS event before I was a director of VETS. And I thought, well, that looks kind of useful. So maybe I'll show you this now. Okay, so now you need to kind of you need to step away from this whole interleaving world. Okay, things just got a lot worse for us, unfortunately. Yes, you can sort of define a little buffer, and then you put the thing in the buffer, and then you can have this model kind of thing, right? That's one way to do it, but that gets super complicated super quickly. Okay, so instead, what you do, what people have done, is come up with sort of what's called an axiomatic semantics. Okay, and what you do is you think about the behavior of a program or the state of a program as being a graph. Okay, and the graph has events. Okay, so reads, writes, and these are kind of read, modify, write events, okay, because we want some synchronization. And the graph also has what's called sequence before or program order. Okay, so maybe I'll show you an example of that in a second. And those are kind of ordering these events according to what the threads say. Okay, there's another relation called the reads from relation, which describes where reads get their values from. So it tags it. You draw an arrow from read to the right, or the right to the read, saying that that's where you read from. And then another one is called this modification order, which is describing the order in which the writes actually occur. Okay. And then you have a bunch of axioms that kind of tell you about different parts of the memory model. So this is getting kind of complicated. Okay, but maybe I'll kind of jump ahead. And what is, okay, so essentially what you're looking for is for validity of your of these relations that you've kind of got. Okay, and the reason it's called an axiomatic or a declarative memory model is you want to know that these 4 properties hold when you draw one of these graphs. Okay, that if I take my SV relation, which is the sequence before relation, and I union it with my reads from relation, okay, then that can't have any cycles in it. Okay, that means that all of the reads that I have in my system come from a write that's also in the system. Okay, so I didn't just randomly make up a read value. Okay, there's a relation called happens before, and happens before describes causality, and the way you kind of get it is by unioning the sequence before relation plus a strengthened version of the read from relation, okay, where you only keep the edges that have what are called release and acquire annotations on them. We'll get to all of this in a second. And what you want is that happens before has to be acyclic, because happens before defines causality, and you can't have causal cycles in your system. Okay. And then finally, you have another one called extended coherence order. So you put together the modification order, the reads from order, and the relation, and the from reads order, which is another relation. Okay, let's maybe skip over that one. And you want that to be irreflexive. And then finally, you have any happens before followed by an ECO is also irreflexive. Okay, so this is just relational composition here, that one. Okay, so that's kind of one way to do it. And what do I want to say here? These are some very old slides, and like I said, I'm making things up as I go. View. Okay. Okay. So I'm going to show you an execution of a program, of this program. This is more or less morally the same as the other program where we did that little exercise. Okay. I'm going to show you that. I wish I hadn't erased it now. So in the previous version, we had something along the lines of if you read this f to be 1, you guarantee that d is also 5. Okay, but we had it it was in a slightly different setting. We had that if, remember we had this implication, right? Remember the implication from before that was on the board. Now, in this C model, okay, the way the program is written at the moment, it's actually possible to get this sort of bad behavior where you read, so this is a read event, okay? You read that f is 1, okay, that's okay. But you also read that the d is 0, okay? So this is because of weak memory. What you're expecting is that if I see 1, remember it was if I see blah, then I see blah, right? What I'm expecting is if I see f is 1, I'm expecting to see d is 5, right? But because of weak memory, even at the language level, okay, what this execution is allowing is, even though I've seen f is 1, I'm somehow seeing an old value of d. Okay, does that make sense? Makes sense. Okay, so what I want to show you is now how to validate this. Okay, using the axiom so far. So remember, what I want is to define this kind of graph, right? I get these relations somehow for free, right? As in, like, they're defined for me. And what I want is I want to make sure that none of these things are true. Okay? So let's see if this execution is valid. Okay, so what I'm first going to do is I'm going to find a modification order. Okay, so this is ordering the writes in the system. Okay, so this is ordering this write up here with the initial write with the write that occurs in this thread. This edge is ordering this initial write to D with this write that occurs here. Okay, that's the modification order. Now I introduce my read from relation. Okay, well, where do I get the value of D from? I get it from up here, right? Where do I get the value of F equals 1 from? I get it from over here. Okay, so that's my reads from edge. So this read reads from there, that read reads from there, and then everything is okay. Yeah? Now there's another one called FR, which I didn't really get into, but maybe I should talk about it now. This is defining the writes that overwrite writes that you read from. Okay, so this write is overriding, because, okay, so think about it. This read is reading from that write. That write occurs after. Okay, so you have a from read edge from there to there. Okay, so that's what happens. And now let's check all our axioms. Okay, so let's check this. I'm deleting the edges that I don't need. So let's check the no thin air axiom, right? Do I read from thin air? Do I read from thin air in this example? No? Right? Because there is a write there in the system from which I actually read. Okay? And you can check that this is acyclic. Okay? Happens before, so remember happens before was this relation here, SB union SW, and SW was reads from with somehow we only keep the release acquire edges. Release acquire annotated operator. We haven't talked about release acquire yet, but we will talk about it in a second. Okay, but we can't see any release acquire annotations, right? So therefore, the intersection is going to be empty. Okay, so therefore, this happens before is just the SB relation, the sequence before relation. Okay. And is it acyclic? Is that SB relation acyclic? Yeah, clear. Then you look at coherence 1, and then this is what the picture looks like there. Okay, but I'm only keeping the relations that I need. Okay, and essentially, it's pretty easy to see that that's acyclic as well. Okay. And then finally, I add this HB as well as the extended coherence relation. And that's also acyclic. Okay? So what does this mean overall? It means that this memory model allows this bad behavior. Okay? So far it's a bad memory model. Okay? Or as in, the program as I've written in this memory model allows this bad behavior. Okay? Maybe it is a good memory model, I don't know. But the program I'm allowed is giving me something that I'm not expecting. Okay? And just to recap, the thing I was expecting is if I read this, I'm expecting to see D equals 5, but I read this and I see the wrong value for D. Right? Because I see an old value because of things that are being left in the cache and so forth. Yeah, does that make sense? Okay. All right. Now we get to release acquire annotations. So I jumped the gun before and I showed you what they were, but I'm now telling you what they are. So this is something you can add to operations in the C model. And you can tag your reads and writes with release and acquire. So release, one way to think about it is like a lock release. Okay, releasing a lock. Acquiring a lock. Okay, so, and you can think of it as if I do this inside a critical section, and then this is the next critical section, surely I should be able to see stuff that happened before this critical section. Okay, it's one way to think about it. But essentially, the way to fix this bad behavior. Okay, now Jeremy said add fences. Okay, that works for TSO. In the setting of the C memory model, what you're given, you do have fences as well, but this other stuff that you're given are things like release acquire annotations and so forth. Okay? So what I have done is I'm taking advantage of this, and I'm now adding a release annotation on my write, and an acquire annotation on my read. Okay? And I'm going to claim that the bad behavior from before is no longer possible. Okay? So here's my bad behavior. Okay? So let's see what breaks. Let's see what breaks when I go through the execution. Okay? So as before, I have all of my edges just as before. Okay? But this time, I have a reads from edge from this read to that write. Okay? But I also have two other extra bits of information. I have that my write is releasing and my read is acquiring. Okay? So you can think of it as an upgrade. Okay? Your read from gets upgraded. Okay? And it becomes a bit stronger. It becomes what's called a synchronizes with relation. Okay? So that becomes a synchronizes with relation. Okay, so in this little program, that's the only thing that changes from before. Okay, because if you remember, going all the way back, yeah, you have this reads from, and you get upgraded whenever you have a release acquire annotation at the end. Okay, so that's what I get. Okay, I'm calling it an enhanced execution even. Okay, so now if I sort of cycle through all of my axioms, I won't go through all of the details. And I look at this coherence 2 axiom. What do I notice? I notice that I've got a cycle. Okay, I've got a cycle from. So remember, I needed HB followed by ECO to be irreflexive. Okay, so here I've got, and remember that HB was SB union SW, right? So I have to go back a bit. Okay, remember HB was SB union SW, right? And then ECO allows this FR edge as well. Okay, so going forward, that's HB, that's HB, that's HB. Yeah, and then that's ECO, that's part of ECO. Okay, and now I have a cycle. And that's bad. Okay, so what does that mean? It means that this execution is actually not possible once I add my release acquire annotations. Yeah, does that make sense? Hopefully you guys are following. Okay, so I'm gonna, maybe I'll even sort of take up the whole 3 hours. Yeah, go ahead, yeah.
Sorry, I was just wondering on the synchronizing bit, intuitively, is it just ensuring that anything that happens, if you think about the order of operations, anything that happens, no matter what reads or write for every variable, is ensured at that point?
That's right. It guarantees that happens before information is propagated. Okay, so that's exactly right. That's a very good way to think about it. We know that this is all sort of happens before information, and this is all propagated to this thread via the synchronizes with. Okay, yeah, it's a great way to think about it. Yeah.
Brijesh,
Any other questions? Yeah.
you're talking about the annotations here to ensure the kind of consistent behavior.
Yes.
Is that something that coders add to their C,
Yeah.
or the compiler adds to the generation?
Coders add to the C.
Oh, really?
Yeah. So maybe I'll look for the link and I'll show you maybe because I'm feeling like I've got enough material now all of a sudden to even deliver the second half. So you talk through the second half, right? Because we've talked about the memory model so far. We've got this Owicki-Gries stuff, and I really want to show you how to connect it all, because that's the really super interesting stuff in a way. Okay, but let me sort of just jump a bit. Like I'm going to show you one operational semantics that looks like this, and to do the other thing I promised, I'd have to show you a different operational semantics, and then maybe I'll also sort of try to answer Jeremy's question, and I'll show you the C manual and what that looks like. Okay. Gosh, there's a lot of material here. You know what? I might not do this because maybe it's worthwhile jumping straight onto the second operational semantics, because this is going to be defunct anyway. See. So I should say standard. Sorry, I haven't prepared this. Let's take a break. Maybe you guys are tired anyways. Let's take a break. We'll come back in half an hour. I'll find the right link, and then we'll link the two things that we see together. Yeah. So is that okay? Yeah. All right. Thanks. Right. So some way of reasoning about the system altogether. Before we get to that, so Jeremy asked a good question before the break about what the programmer has to do, and this is the C++ reference, one of the pages from the C++ reference, and you can see that some of the things that I've talked about are there on the screen. So when you write your code, and if you're using C++ atomics, you can annotate them using an acquire, using a release. We talked about relaxed as well. So relaxed was when we had no annotation, we were assuming relaxed. Okay. There's also another one called acquire release, and there's another one called sequential consistency. We didn't really sort of talk about that. Acquire release you use when you've got a read modify write operation, and you can tag it with an acquire release, meaning that it performs both as an acquire and a release, and it's a read modify write operation. Okay, so it's very strong. And then there's this other order called consume order, which we won't get into because it's not used that often. But yeah, the stuff I'm showing you is real. Okay, that's what I wanted to kind of wanted to say. And unfortunately, the programmer, the programmer, is responsible for using these correctly. Okay. How annoying it is to have to write correct programs. Okay, so I spent a bit of time talking about these coherence orders and various orders and the axioms and so forth. Okay, but where we kind of want to end up is in a world where we could actually do some theorem proving. Okay, and you saw in the other slides that you end up with lots and lots of inductive relations, or inductively defined relations, right? So transitive orders, you cared about whether things were cyclic or irreflexive and so forth, right? And there has been a big attempt at sort of getting us away from that, and instead of thinking about memory models in that way, in the sort of axiomatic style, to think about them using what's called a view-based semantics. Okay, so it's a different semantics. And it's based on this idea that threads have an observation of what the state is, okay? And based on their observations, they can kind of make inferences about what's going on in the execution. Okay, that's kind of this idea. And there are sort of proofs of equivalences between the other semantics and this one as well. Okay, so we've seen this program here. This was the message passage program. We've done an exercise around it. It's slightly different again. Okay, here on this page, and we saw that in our bad or poorly annotated program, you could end up with this as a post condition, right? That although this loop only terminates once you've seen 1 for f, right? So this loop only terminates 1 for f. You can kind of get to the end of the loop and then still see the old value for d, right? That was the example we were looking at before. And we said the way to fix it is to add release acquire annotations, right? So when we're performing this this write, we add a release annotation, and when we're performing read, you add your acquire annotation, and then we saw that that gives you the synchronizes with edge, and that then allows you to prove that the information from this thread is propagated to this other thread, which means that when you read the D to load it into R2, you get the correct value, the expected value. Okay, everyone happy with that? That was just from half an hour ago. Yeah? Okay. So, so another way to sort of think about this is to, well, we have those graphs, those very big graphs, and it was all very complicated, and you can imagine that, you know, once you have some decent sized program, you're going to sort of run into scalability issues for sure, right? Because there's so much stuff, so much information you need to track. Now we're going to sort of talk about another way to think about this in the setting of this view-based semantics, okay? So the way we're going to kind of think about this is, well, what's really going on? What's really going on here? We've got a thread that's executing, and it executes these operations in some kind of way, right? So you're sort of interleaving these operations in some kind of way. And information may or may not get passed along. That was a good point that you made earlier about the synchronizers with edge and how it sort of passes along information, right? So information may or may not get passed along from one thread to the other through a read, right? So if you have a release acquire annotation, information does propagate. If you don't have the release acquire annotations in the right places, the information doesn't propagate, okay? So, so here, for this read to have read this write, certainly we needed that information to have been propagated there, right? Otherwise, this read would see the old value. But somehow this information is sort of propagated much later. Okay, that's kind of the reordering that you're getting. But over on this side, you don't get that problem because you've got sort of release acquire annotations. Things stay in order. Okay, it's one way to sort of think about it. And with that in mind, well, in particular, I think Victor Vafianis and his group and Ori Lahav and people at NPI, I think they were mostly responsible for this sort of view-based idea that you can kind of think about your semantics in a very different way, a slightly different way, maybe. I don't know. Depends on what you depends on how you grade these things. Okay, but we think about now as the systems as having various views, threads having various views of the state. Okay, and the views sort of changing as the execution evolves. Okay, so I'm going to step through this program here, the BAT program. This is the one without the annotations. And I'm going to sort of show you how the views evolve as the program executes. Okay? So threads have a view of all the variables in the state. Okay? And all of the variables in the state are kind of ordered, totally ordered, right? So each variable is totally ordered. So with values. Okay, so this is saying we have an ordering for D and we have an ordering for F. Okay, the values for F, and then this is the initial state essentially, right? So the only values that D and F can take are 0, and we have a point in time at which they occurred. Okay, make sense? And then what can the threads see? Well, initially, they can only see the initial state, right? So this is thread 1 and thread 2, and they're seeing this state here. Okay, so they both see 0, 0 for D and F. Okay, makes sense. Okay, so now let's execute the left thread. Okay, so because thread 1 was the thread that sort of took the step, obviously it's going to know about the new value for D, right? So what happens is, and also we know that, well, values can get inserted in the middle, but that doesn't matter. What's happening is that there's some total order on the rights of D, right? And this 5 happens after, and so you kind of have the thread 1 has seen that D is here. Okay, that's the value for D that it can see. Thread 2, its view, it doesn't know that this has happened. Okay, in a sequentially consistent world, so in a world with no caches and so forth, all of the writes go straight down to memory, right? And then the other threads read from memory, right? So everyone sees like a very consistent view of what the world looks like. But now you've got all these sort of caches floating around, right? So these buffers floating around, and threads don't know that stuff is happening on the other threads. Okay, so one thread. So this thread, T2 has no idea that this write has happened. Okay, so we're giving it this. We're adding some non-determinism here. So we're saying that thread 2 could either see that or it could see that. Okay? But the point is that, yeah, the point is that it's sort of lag. It's understanding of what the world is lagging. Yeah, does that make sense? Yeah, okay. So if I now execute the next assignment, which is this one here, what's going to happen? Again, thread 1 is the one that performed the operation, so it knows about this this new value. Okay, we've got a total ordering on the writes to F. Okay, and thread 2 is still oblivious to all of this. Okay, thread 2 has no idea this is happening. So it's non-deterministic in the sense that in this state, it's allowed to read either 0 or it's allowed to read 1. Okay, for F. Okay. So let's now, because it's non-deterministic, we're allowed to pick whichever read you read, but let's look at an execution where this loop terminates. Okay, and this loop terminates when does it terminate? Okay, maybe I can ask you this. When does it terminate? Yes?
When the T2 view updates.
Exactly, yeah. So it terminates if thread 2 reads F as 1, right? Which means that its view must have been shifted this way, shifted along, okay? So that's good. The bad thing is that we didn't propagate any other information here, okay? The bad thing is we don't know anything about D. Thread 2's view for D is still way back here, okay? So now what this allows thread 2 to read both 0 and 5 for D. Yeah? Just like before. So you end up with D, so even though this loop terminated, this D could be either 0 or 5. Okay? That's how the semantics works, roughly. There are lots of other details, of course, because it's formal methods, but yeah, that's roughly how it works. Now let's see what happens if we add our favorite annotations or release acquire annotations. Okay? So again, we're looking at an execution where thread 1 first goes and then thread 2 goes. So, okay, so that's as before. Execute this D is assigned 5. Now we execute this right here. Okay. Now what we're going to do is we're going to tag the value itself with some annotation. Okay, and there's going to actually be a view that's not actually depicted on this slide, but one knows that thread, one is going to kind of inherit, this value 1 is going to inherit the view of the executing thread. Okay? So there's a, in the maths, there's a mapping from here to here, this event to this event. Okay? But think of it as this inherits the view of the executing thread. Okay? So what that means is when you perform this acquiring write of a value that is releasing, you inherit that view. Okay? So essentially, just to sort of say that again, this write, it's first of all, it's tagged with the releasing tag, but it also knows, it's got a record of the view of the thread that executed that write. Okay? So it's got a record that D is 5, because that's that thread's view. Okay? And now when this thread does this acquiring read, it somehow inherits this view. Okay, so before we didn't get that inheritance. Okay, here we didn't get that inheritance. But this time, the math says, or the semantics says that you have to inherit this new view. Okay? And because you've now inherited this view, there's no chance of reading 0 anymore, because it's in the past. Okay? Does that make sense? Makes sense. Okay, so this is sort of this view-based semantics. Okay? And here's what it looks like. No one wants to read this, right? Maybe if you're a popular reviewer, you'd like to read this. But what we're essentially doing is we're breaking down our program, and we're extracting actions or actions from it. So this little A here. Okay. So for example, if you've got a write statement, you're extracting a little action A, which is a write action. Okay. And if this happens to be a releasing write, then you get a little releasing tag. Otherwise, you get nothing. Okay. For a read, so this is reading from X and loading it into the register R. Okay. You execute this, and this is one operational step. And the corresponding action is going to be a read, and you may or may not have an acquiring annotation, depending on whether the syntax that you're executing has a acquiring annotation. Okay. And then there's a sort of read, modify, write operation, which we're calling update for some reason here, and it's kind of similar. So these are kind of the atomic statements now. Okay, so in the Hoare logic, we only had 2 things to worry about. We had skip and assignment, right? Those were our 2 atomics. And now we really do care if in this atomic statement we're performing some kind of globally visible action. Okay, so we're kind of, you can think of it as we're splitting up assignments into, this is updating some globally visible X, right? So it's a shared memory X that's being changed, and this is a shared memory X that's being read. Okay, they're both kind of assignments really, but one's kind of like, one corresponds to reading from this sort of shared memory, and then one corresponds to writing to the shared memory. Okay? And then there's the other atomic, which is the swap, which corresponds to read, modify, write. We won't really get into that. And then you have, just like before, oh, I can do this. Wow, that's great. Then you have this. Things you discover accidentally while you're giving a lecture. So those are your sort of compound statements, just like before, right? Sequential composition, if then else while. And then you also have sort of auxiliary, these auxiliaries here, right? And then your parallel composition and so forth. Okay. Okay. Now this gets a little bit hairy. Maybe it's not worth spending too much time on this. I can go over it if you want. Like, what would you like to do? But maybe it's worth kind of getting a flavor for what's going on here. So we've got this bit of the semantics that extracts actions from syntax. Okay? Now we need another bit of the semantics that tells you how the actions affect the shared state. Okay? And the shared state comprises, gosh, it's not here. Comprises just a bunch of functions that tell you about these views. Okay? So there's a thread view, and that's the view that we've seen. Okay? And it's telling you about kind of the, so there's T view here, this is the thread view, okay? So that's basically it's modeling this thing. Okay? So it's a function from a thread to particular rights. Okay? Then there's this, what's called a modification view, okay? And that's a function from, like I said here, we need to keep track of the fact that at this point, it has to kind of inherit this view, this thread view, okay? So that's kept track of using this modification view. So the modification view goes from write events to a thread view. Does that make sense? So, because you want to know when you perform that modification what the thread view was of the executing thread. Okay? So that's what that is. Maybe it's actually not that bad. So it's a modification view goes from, so this is the write event, and it goes to a thread view. Okay? And then obviously this is the set of rights, and then there's another sort of technicality called cover to do with read modify write. We don't have to go into that. Okay? But now let's look at sort of what happens when you execute a read. Well, what happens? What happens is, well, you're either executing a relaxed read or an acquiring read. Okay? Now, you must be reading from some right that is observable to you, okay? Some right that's observable to you. And that's what this is saying. I haven't given the full definition, but in essence, so at this point, the observable rights for thread 2 of D would be both of these. Okay, so those would be the observable rights. For thread 2, for F would be both of these as well. Okay, that's what the observable rights are. Now in this state, I can't get rid of that anymore. The observable rights for thread 2 would be just that, and for thread 2's, for D would be just that as well. Okay, so it's telling you what you can actually read from. So like, which rights are valid for the thread to read? And it's saying, pick one. Pick one of the rights that you can read from. Okay? And this is the value that right has. Okay, that right has that value. And now I need to know how to update my thread view state. Okay, if you happen to be in release acquire synchronization, okay, if it happens to be the case that you are performing an acquiring read, and the thing that you're reading from was a releasing write, then you do this sort of merge of the views. Okay, so you get this view update here that's kind of quite complicated, but you're essentially getting the view of the thread, the write that you read from. Does that make sense? And you inherit all of that information, so you sort of suck it up and you say, my new thread view is going to sort of inherit all of that information. Okay? If it happens to be the case that it was not a release acquire synchronization, either because you were not an acquiring write, not an acquiring read, or the thing that you're reading from is not releasing, then you just do a simple thing saying you update your view for that variable to that write that you read from. Does that make sense? That makes sense. So you either synchronize, in which case you have this view update, or you don't synchronize, where you just say, oh, I move it to I know about this variable's value. Yeah, go ahead.
Is it possible that in the thread with the right, there is an outdated version of another variable, and you that are doing the read have a more updated version? In the case where you synchronize, do you continue with the more updated version of the right?
You always get the latest version. So that's what that cross is.
So it just synchronizes all the ones that were previous versions of that. Of
Yes. It's the maximum view. I think. Yeah. Good question. Any other questions?
So an acquiring read can also read from a normal write.
Yes.
And there's simply no synchronization.
Exactly.
Allowed.
Yes. Yeah. So you could read from a normal write, and then no synchronization happens. Okay. And if no synchronization happens, then you're in this. You just sort of simply update your thread view, but you don't get any other information from there. But only when there's this sort of release acquired that you get this merge of the views. Okay, and merge as sorry, I don't know your name. Merge as was pointed out, it's about getting the maximum. Okay. Writes, well, writes. Okay, so the thread that performs the write has to. It definitely knows about this new write. Okay, that's what this is saying. The write. We in this particular model we don't really differentiate between acquiring writes and releasing writes and not releasing writes. We just say that the write always acquires the thread view. Okay, or the write always knows about that thread view. So that's what that bit is. And then this is just saying that I have a new write in my system. Okay, so it's fairly straightforward. There's a sort of technicality to do with covered, but I'm not going to get into that. Okay, and then this is sort of saying, because the way the total order is kind of managed is using timestamps. Okay, so all of the writes have a timestamp, and that's what this is. And this is saying pick a fresh timestamp for the new write that I'm about to do. Okay, that's read modify write. Okay, it's complicated, but really what's going on is it's just merging the two rules together, because the read modify write does both a write and a read at the same time, and it's an atomic operation. So that's why this looks complicated, but it's actually really not that bad. Okay. All right. So now that we've gotten through that slide, we can now kind of start thinking about semantics of programs, and you essentially put the memory model semantics and the syntax semantics together. Okay, so one of the arrows generates these A's, these actions, and the other arrow tells you what to do with the actions. The squiggly arrow tells you what to do with the actions, and then that's what's going on. Okay, over here. Okay, so we're getting close. We're actually getting pretty close now to being able to do the thing that we said we wanted to do. Okay. So now we have this sort of this idea of a state, and before we said our state was going to be. So I think Nat said this. A state was a mapping from. So we said our sigma was ID or location to value. Okay. Let me just duplicate this. So this was in SC or sequential consistency. Okay. That's what we said. So we said sigma is ID to val, but we're assuming a sequentially consistent memory model because all we have is this sort of shared memory that's there. Okay, but now we have something more complicated. Okay, so we're going to now get another kind of notion of a state. So this is like, let's call this a sigma weak memory, or to be precise, this is the sigma C11 state. Okay? And what does it have in it? Well, it has this, it's got this thread view function, right? What else does it have in it? What else does it have in it? So it was from the previous slide, right? So, anyone can read that? So the CAS is modifying all of it. Let's forget the covered bit. So don't worry about covered. What else does it have? So it's got the thread view, right? What the threads can see. What else does it have?
What was the end view?
So that was the modification view. So what the writes can see, right? So it's got this modification view. Okay. And it's got the set of writes. Okay? And if you really think about it, so actually we don't need these brackets. We don't really, when we're executing our operational semantics, that's all we're doing is, instead of modifying states of this nature, we're modifying states of this nature, right? And, you know, if you stare at it for long enough, that's exactly what's happening. You're saying that you're getting a sigma that is of that type, that C11 type, right? Little sigma that's of this sigma C11 type, and it's being changed to another sigma of another C11 type. And all that's happening is that these functions are being updated, right? So there, in the read, the only thing that happens is that this component gets updated, right? In the write, what happens? The thread view of the write changes, the writing thread changes. You get a few more updates, a few more things that change. Okay, so it's kind of neat now, right? Like it's kind of, maybe this is something that we can reason about. So our state sigma, we're now going to think of it as being of one of these elements. Okay, one of these guys. And what does that mean? What does that mean? So we had this before. Okay, let's call this C11 here. Okay, and so we had this, and now we've got this. That's the only thing that's changed. What should we be able to do here? What should we be able to do? Can we develop a Hoare logic / Owicki-Gries logic? And if so, how? Okay. So what do we have in the Hoare logic? In this sort of, what do we need to know? We need to know what predicates are, right? And what was the type of a predicate? Do you remember? Does anyone remember? Sigma to bool. Right? It tells you whether or not a state belongs in that predicate. So this was our old setting. This is our new setting, right? Our predicate was of the type sigma to bool. Okay. Can we do something similar? I mean, what is a predicate? What is a predicate?
Statement about the state.
It's a statement about the state, right? It tells you, for a state, whether or not some property holds or not, right? you can use a predicate to tell you, say, is x less than y in this state? Okay? You believe that, right? That was from before, and you said you. So what do you think we could do over here? What kind of predicate do you think we could write here? Let's do a fancy P. Okay. What kind of predicate should we be able to write?
Still one from state to bill, right?
Sorry?
Still one from state to bill, just with the new type of state.
With the new type of state, exactly. So we're now going to have a fancy predicate. Let's call it C11. Let's do this. But it's going to go from there to there. Okay? So it's basically nothing has changed. We have is going to go from, okay? Okay, that's all that's happened, is that I'm now going to be, I know what a state is, okay? I just need a way to talk about views and how views change and so forth, okay? And before I had a language, a predicate language that had things like, I don't know, equality, operators like equality, less than, whatever, plus, minus, whatever. Okay? But I need a little bit more here. Okay? So I have all of that stuff, but I also now want to be able to talk about things like the view of a state, a view of a thread, or the view of a right, and so forth. Okay? Because I want predicates that tell me something about these components. And the rights is actually not even that important. It's these two components that really come into play. Okay? So I'm going to invent some notation to do this. And the interpretation of the notation is going to go right down to the state, and it's going to tell me exactly how this sort of unfolds. Okay? So I'm going to invent this notation x equals v for the thread t to mean the thread t must observe the value v for x. Okay, so it's the last write. It's looking at the last write for that x for x. Okay, make sense? Yeah, maybe. Yeah. This notation here. Yeah, because I've got sort of in my C11 state, I've got thread views. I can say things like thread t may, and this could be true, or may not be true. Okay, thread t may observe the value v for x. It might is another way to say it, sort of more accurately. Make sense? Yeah. So this is looking a bit modal. It's not. They're not kind of duals of each other. If you're thinking, oh, are they dualities? They're not. They're not quite. Annoyingly, I wish they were, because that would be nice. This one is a bit strange. This is what we call anyway, a conditional observation. Okay, you're in such a state that if you were to read the value v for x in an acquiring read, then you would see that after that, y is definitely equal to w. Okay, so it's kind of a conditionally. So if this thread t sees that value for x, you're going to be in a state where, because of all the synchronization that happens during the read, you're going to be in a state where you definitely see that y equals w. That make sense? Yeah? So, I don't know, if you're following, okay. So say that's my state, okay? And say that was T1. D equals 5. So this is just a box kind of notation, right? True or false? Does that assertion hold for that state, or does it not hold for that state? True? Yeah? So in this state, if thread T1 reads D, it is definitely guaranteed to see 5. Right? The value 5. Okay. What about this one? True or false?
Well, false.
False. Because?
I mean, if nothing else, it's mutually exclusive with the truth.
Okay, but okay, fine. Now let's use the other brackets. Let's use the other brackets. D equals 0 for T2. Yeah. True or false? Yeah, it might read 0. Yeah? Might read 0. So this was true, this is false. T2, true or false? True or false?
True.
True? Yeah, so they're both true in this case. So it could read 0, it could read 5, okay? But it doesn't read 7, okay? Okay, good, so you guys are kind of following along. Yeah, that's great, okay. But do you see where this is going? Do you see where this is going? I've got an operational semantics, I know what a predicate looks like, I've got an assertion language, okay? Do I have all the ingredients I need for building an Owicki-Gries logic? What's missing? Sorry? We have the rules. We know what an Owicki-Gries logic looks like. Is anything missing? That's maybe a trick question. Is anything missing? No. Okay? So I could even stop here and say, you do the rest for yourself. But I'm not going to. Okay? You can do, we have all the ingredients we need to build an Owicki-Gries logic. Okay, we have an idea of what states are. We know how states are modified. We know what predicates look like. Okay, so we can do it. Okay. Now this is message passing. It gets a bit worse. Worse in the sense that your assertions are a bit more complicated than before. Okay. Okay, by the way, given that you guys are following, I'm just going to ask you one more question about this conditional observation. So this one here. Okay. True or false? Oh, that is true. Okay, but why is it true? Can you think about why that's true?
Because there's a release on the 1, which
Yep.
means that for that read to may have happened, means that it has to be impaired to be from T1.
Exactly. Yeah. So in this particular, well, I haven't given you the mod view, so that's a little bit kind of unfair, maybe. But it's saying if I read 1 for F through an acquiring read, I'm guaranteed to update my view to get D equals 5. Okay, and you can see that here. So so this is the bit where that conditional observation holds, right? So the state after, so this is the state before, the state after is going to be the state here. Okay, because I get this merge of the views from the state. Okay, so that's what that's saying. Okay, and that assertion is kind of critical for the message passing example, which is the one we've been looking at several times now. Okay, so let's write down some assertions, but we're going to do it this time. We don't have equality. We have these views absolutely everywhere. Right? It doesn't make sense to say this location has this value anymore. What we can say is this thread can see this value for location blah. Okay? So initially, what do we have? We have thread 1, if it reads 0, if it reads D, it's going to see 0. If it reads F, it's going to see 0. And that's the same for the other thread, right? If thread 2 reads D, it sees 0. If it reads F, it sees 0. Okay? That's just sort of, I definitely see this value thing. Okay, and there's the rest of it. Maybe I should, I mean, given this, if I prepared this earlier, I would have done this maybe more slowly. But the point is you kind of need some assertions about what the other thread can see at some point. Okay, so but these all have meaning. Okay, and you've seen what the meaning is. The point is here, thread 1, you get this as an implication from up here. Okay, and now if I perform this assignment, I get this as being the next assertion because thread 1's view is updated to 5. Okay, but there's no f equals 1 anywhere, so there's no way that thread 2 can see f equals 1. Okay, so you kind of get this this being propagated, and that's the reason you need that information is because of the interference that this interferes with some of the assertions on this side. Okay, just as we had before, and after that, we kind of don't care what the state is, so we just write down the weakest possible condition there. Okay. Here we have this sort of conditional observation property, and it's a bit weird, but the initial state does guarantee this. Okay, because what happens is that the left-hand side of the condition becomes vacuously true. Right. In the initial state, there is no f equals 1, so you have this conditional observation was something along the lines of, if I see f equals 1, then something happens, right? But the if becomes false. The if part becomes false. So you get that condition for free. And then there's a condition, there's an axiom that sort of tells you how you go from here to here, and here to here, and so forth. And then you kind of get this, you get basically a Hoare logic proof, okay? Because we have all the components. And okay, and then this one is interesting. So this one is saying if thread 2 reads the value for 5 for D, then it sees, if thread 2 reads D, it definitely sees 5. So what you can assert after that is that R2, the register R2, definitely has the value 5. Okay, and then you get your final post condition. Okay, so that's all of the ingredients we need. The only thing I haven't shown you is the soundness of these rules. Okay, so the only thing I haven't shown you is so in Hoare logic we had two axioms for the atomic statements. That was for the skip statement, and then we had so we had these axioms, if you remember, right? This is what you've seen in probably undergrad as well, right? Just repeat it on this side. So we had P, skip, P being one axiom, and another axiom was P x aside E gives you back P. Okay, that was the axioms, and you take them as axioms, but of course you got to prove their soundness. Okay, and there are ways to prove their soundness. But here we have, pretty much the same thing, right? We know what assertions are, we know what preconditions are, we know what the execution of a program does because we've got the operational semantics. Okay, but the problem is that we have differentiations between the assignments, right? Depending on what you're doing in the assignment, are you loading from a shared location? Are you writing to a shared location? You end up with a big long set of axioms, annoyingly. Okay, but it's not too bad. It's not too bad, and you can prove each of these sound. Okay, does that make sense? Okay, but yeah, these are sort of axioms that are sound for the logic. Okay. Gosh. I'm almost done. Almost done. Yeah, I think I'll stop there. Okay. So I'm almost done. I only want to show you one more thing. It's the last day, and I guess people get tired and so forth. Okay. Just to show you that this is all very mechanical, and that this is all the logic works. Okay, just to sort of for you to double check that. You can code this up in Isabelle, and we had so in Isabelle there's it ships with the Owicki-Gries logic as a theory built in, but that's for sequential consistency. Okay, so what we needed to do was change this idea of what the state is. I don't know why it's called, well, it's called Surrey state because it was developed in Surrey, but that's the sea level. That's the sea level state down there. Okay, and if I poke inside the Surrey state, I'll see that it's a record that's got the thread view. Okay, so it's got some other stuff in there as well, but the important bits is that it's got the thread view and the mod view functions. Okay. Thread view is sort of taking a thread and giving back a view, which is this thing here. And the mod view is taking a location with a timestamp and it's giving back a view, which is this thing here. Okay? So that's how that bit works. And then you can kind of encode the, this is the write transition, and it's sort of telling you how the views are being updated. This is the read, modify, write, which has lots and lots of things that are being updated and so forth. And then so you kind of have some helper levers and so forth in there. That's disappeared all of a sudden. Now this is the definite observation property, which is this this one here, the square brackets. Okay. We decided to change the diamond to a squiggly arrow, but the squiggly arrow is the diamond. A squiggly equals is the diamond. Okay, it's the may observe or might observe kind of property. And then this is the conditional observation thing. Okay. And the T's are sort of moved around a little bit, but okay, fine. It's more or less, morally, it's the same thing as what I showed you before. Okay. And then finally you have, sorry. God, what happened? Finally you have a proof outline that you can write in Isabelle. Okay. So this is the message passing example from before. Exactly the same. Okay. You have your assignment to D, you have your assignment to F, that's a releasing, right? And then you have your acquiring read from F, and then you have your read from D, and this is inside a loop. And I wanted to show that at the end that R equals 5, right? I wanted to prove that. And because Isabelle ships with this Owicki-Gries logic, we can kind of reuse it. And this tactic here, this Hoare tactic, essentially splits up. So you can kind of see. Oh, if I can remember how to do Isabel. Can someone help me? Isabel, folks.
Apply rule.
Sorry?
Apply rule.
Apply rule?
Yeah, the parentheses after the apply.
I forgot my Isabel. Yeah, okay. Stays. Yeah, there we go. Okay, so that breaks it up into the OG. When you apply the OG Hoare tactic, it breaks it up into all of the little components that we have to prove. Yeah? And then I can go simple. Okay. So that was a big long list of 41 sub-goals, and then Sibs just sort of throws away. Okay, and so forth. And then one of the things Isabel has is the sledgehammer thing. So if you didn't know how to sort of prove, okay, so hopefully this one is sledgehammerable. Let's see. Live demos never work. Didn't quite work. Okay. No. So let's say I didn't have. Let's say I did this. Gosh, it just does everything automatically in one line. I'm trying to sort of show you how it does it. It doesn't do it automatically in one line, but okay, whatever. Quite often, if you're stuck, you can just call sledgehammer, and what it does is it goes and looks for the correct axiom to apply. Right? By axiom, I mean these ones, because there's a big long list of them. Okay, but the sledgehammer will go and find the right tactic to apply, and then it applies it, and it sort of helps it discharge the proofs. Go along. Okay, so that was my fill-in lecture for David. Hopefully you got something out of it, but I kind of wanted to show you where we are with where we were a few years ago on this sort of deductive verification of weak memory programs. Okay, but I'm kind of hoping one of the takeaways you got is that it really isn't that hard to build an Owicki-Gries logic once you have the components, right? The components being an operational semantics and an interpretation or some kind of notion of what assertions look like for these weak memory states. Yeah, because that's what you're going to get. You can actually do this reasoning entirely in that other sort of axiomatic style as well, but the Isabel really doesn't like it because you need to build lots and lots of. I guess Jamie, you're an expert on Isabel. Maybe some of the others are also interested, experts. But once you sort of start dealing with sort of closures, relational closures, it sort of really, it really sort of doesn't like it, or sledgehammer certainly finds it difficult. Okay, but yeah, so I think sort of the two takeaways that I'd like you to sort of walk away with is this is the state of the art for. Well, this is one of the sort of lines of deductive reasoning for C11. There are other memory models out there, but you can build Owicki-Gries frameworks around it. Okay, that's all I wanted to say. So thank you for listening. I guess that concludes the summer school as well. So hopefully you had a good time. We'll be back next year. I think we might be going to Exeter next year. So by the beach. Bring your dogs. Yeah, and if you have any questions, feel free to come up.